Welcome to the Deep Dive. Today, we're tackling a challenge that's absolutely critical for any AI model to make a real impact: inference. You might spend countless hours training incredibly sophisticated AI models, but the true magic, the actual utility, well, that happens when those models are deployed to make predictions in the real world.
Precisely. This is where the rubber truly meets the road for AI applications. Our sources for this deep dive, they come from excerpts from Mastering TensorRT, High-Performance AI Inference, and TensorRT, Optimizing AI Inference with NVIDIA GPUs. Our mission today is really to equip you with a foundational understanding of how to make AI models not just work, but work incredibly fast and efficiently, especially on NVIDIA GPUs.
That sounds like a mission critical for anyone building AI. So let's dive right in then. What exactly makes inference its own unique and, well, formidable challenge, separate from, the intense computational demands of training?
Yeah, what's fascinating here is that while training is all about learning from massive data sets, inference is about applying that learning, applying it efficiently, lightning fast, with minimal resources, often in real-world scenarios. The core problem, the big tightrope walk for engineers, is balancing performance, accuracy, and cost/power efficiency. You can't always have it all.
So you're saying it's a constant trade-off, a balancing act. What are the practical pressures that make this so difficult?
Exactly. I mean, think about an autonomous vehicle. Every millisecond counts for decisions, right? Pedestrians, other cars. That's latency. The time it takes to get a single prediction is just paramount. High latency means the application is simply unusable. It's too slow.
Right.
Unusable, or consider a massive data center serving, millions of users. The goal there is often throughput. Maximize the number of inferences processed per second. That directly impacts your operational costs and how many users you can actually serve simultaneously.
Okay, so speed for one versus scale for many.
And then, especially for tiny edge devices, maybe a smart camera or something, it's all about cost and power efficiency. Minimizing the hardware footprint, minimizing power draw. That's crucial for accessibility, for sustainability.
That really drives home that it's not just about the model itself then, it's the whole system around it.
That brings up a crucial point. Successful model deployment, it's a comprehensive systems engineering problem. It really is. An inference pipeline isn't just the model running. It involves data ingestion, pre-processing, post-processing, and deep integration with all the surrounding infrastructure.
Like what kind of infrastructure?
Well, things like containerization with Docker, maybe orchestration with Kubernetes for managing scale, multi-zone cluster management, load balancing. It's about a highly coordinated, well-architected system, not just the standalone piece of code.
Okay, so if inference is such a complex systems problem, how does NVIDIA TensorRT fit into this intricate picture? Where does it come in?
Right. So TensorRT is specifically an SDK. It's a software development kit for high-performance inference optimization and runtime. And crucially, on NVIDIA GPUs, it's not for training. It takes your trained model, its neural network architecture, and then it generates this highly optimized deployable engine that runs super fast on NVIDIA hardware.
An engine, okay.
And by focusing exclusively on inference, TensorRT can apply really aggressive hardware-specific optimizations, things that just aren't feasible during the more generalized training phase.
Aggressive optimizations, that sounds incredibly powerful. Can you give us a sense of what these actually involve? Like, what's the secret sauce?
Yeah, it's pretty fascinating how it achieves these speedups. It really boils down to 5 core pillars. First, precision calibration. This is about reducing the numerical precision of your model's weights and activations.
So using fewer bits?
Exactly. Instead of the standard 32-bit floating point, FP32, it targets faster formats like FP16, half precision, BF16, or even INT8, which is 8-bit integer. And this is a game changer because these formats leverage specialized Tensor Core hardware on modern NVIDIA GPUs.
Tensor cores, right? I've heard of those. Dedicated hardware units.
Precisely. Think of them as dedicated matrix multiplication units built right into the GPU. They supercharge the very operations AI models rely on most heavily. Second pillar, layer and tensor fusion.
Fusion, like combining things.
Yeah. Imagine your model is like a series of steps. TensorKey can combine multiple individual operations, maybe a convolution, then adding a bias, then a ReLU activation into a single custom CUDA kernel. This vertical fusion reduces overhead and, crucially, keeps intermediate data in fast on-chip memory. It avoids those slow trips to off-chip memory, which is often the biggest bottleneck.
Keeping it local on the chip.
Smart. It can also do horizontal fusion by combining layers that happen to share the same input. Third, kernel auto-tuning. For any given operation and your specific target GPU, TensorRT has a whole library of pre-implemented CUD kernels.
Different ways to do the same math.
Kinda, yeah.
Yeah.
And it actually benchmarks these on your hardware during the build phase to select the absolute fastest one for that particular operation on that GPU.
Wow, so it tunes itself to the specific card.
Exactly. Fourth pillar is dynamic tensor memory. This isn't just about saving memory overall, though it does that. It's about optimizing how memory is allocated and reused during inference. Reduces the footprint, increases efficiency. And finally, fifth, multi-stream execution. This enables parallel processing of multiple independent inference requests, really maximizing the utilization of your GPU, squeezing out all the performance.
That makes perfect sense. It sounds like TensorRT is essentially rewriting parts of your model's graph, tailoring it to fit the hardware perfectly. So how do developers actually interact with this? Do they need to, learn a whole new programming language?
Not necessarily. Developers can use the TensorRT core library directly. There's a C++ API, a Python API, that gives you fine-grained control, great for deep optimization. Or, for convenience, there are framework integrations, things like Torch TensorRT or TensorFlow TRT. These let you use TensorRT more directly within your existing PyTorch or TensorFlow workflow.
Okay, so options there.
But honestly, the most robust and flexible workflow for production, the one we see most often, involves ONNX. That's the Open Neural Network Exchange.
ONNX, right, the universal format.
Exactly. It's framework agnostic, like a universal translator for neural nets. You can export your trained models from, say, PyTorch to ONNX format. Then you use TensorRT's ONNX parser to read that ONNX file and build the optimized TensorRT engine. This decouples your training framework from your deployment engine, which is a really key best practice in modern MLOps.
Decoupling. That sounds like good engineering. And what about deploying these optimized models at scale? Is there more to the ecosystem beyond just the core TensorRT engine itself?
Absolutely. There are specialized libraries, too, like TensorRT LLM, which is specifically for accelerating large language models. It has LLM-specific optimizations like in-flight batching, super important for conversational AI. Then for deployment runtimes, you've got NVIDIA Triton Inference Server. That's designed for managing and deploying these engines at scale in production environments, handles requests, batching, all that stuff.
Okay, Triton for serving.
And for end-to-end video analytics pipelines, there's the NVIDIA DeepStream SDK. So you can plug your TensorRT engine right into a video processing pipeline. These tools really round out the whole ecosystem, taking you from optimization to actual deployment.
Okay, that gives us the big picture. Now let's unpack that core TensorRT workflow you mentioned. The sources talk about a two-phase philosophy, build and runtime. What's the distinction between these two, and why is it important?
Yeah, this distinction is absolutely key. It's fundamental to how TensorRT gets its efficiency. The build phase is where all that optimization magic we just talked about happens. All the fusion, the precision changes, the kernel tuning. This is typically done offline. It can be quite time-consuming, sometimes minutes or even longer, because TensorRT is exploring tons of optimization strategies and benchmarking kernels on your actual hardware.
Okay, so you pay the time cost up front.
Exactly, and the result is a serialized file. It's often called a plan or an engine. You save this file to disk. Think of it like compiling a highly optimized executable specifically for your model and your GPU. Key Python API objects here. You've got trite.logger to see what TensorRT is doing, trite builder, which is the main orchestrator, trite.ibuilder config for setting options like precision modes, .trait.network definition where you define the network structure, usually using the explicit batch H flag these days, and trite.onX parser if you're starting from an all-in-X file.
Got it. Build phase.offline, slow, creates the optimized engine file. What about runtime?
The runtime phase, on the other hand, is designed to be extremely fast and have very low overhead. This is where you load that optimized engine file from disk and actually use it for inference on new data. This is the execution part. Key Python API objects here are trait.runtime, which you use to deserialize your saved engine file. Then there's the iCUDA engine itself, the loaded engine, and crucially, the iExecution context. This provides the context for running a specific inference task. You can create multiple contexts from one engine, which is how you get parallel processing.
That makes a lot of sense. Prepare once, execute lightning fast many times. Can you walk us through a quick hands-on example, even just conceptually? How would a developer go from a trained model to running inference with TensorRT?
Absolutely. Let's imagine you have a standard ResNet 50 image classification model. Say trained in PyTorch. Step 1, export to ONNX. You use PyTorch's built-in torch.onNX.export function. You give it your model, a dummy input tensor so it knows the expected input shape, and specify an offset version. This spits out a .onX file.
Okay, model is now in ONNX format.
Step 2, build the tensor engine. Now you use the TensorRT Python API. You'd start by creating a trot logger, just to see progress and warnings. Then you create a trot builder. Use the builder to create network, making sure to set that explicit /batsiege flag. Then you create a trot onX parser and tell it to parse your .onX file, populating the network definition.
So it reads the blueprint.
Exactly. Next, you create a builder.createBuilderConfig. This is where you set options. Like you might specify a workspace memory limit, say 1 GB, which tells TensorRT how much GPU memory it can use during the optimization process itself. Finally, you call builder.buildSerializedNetwork, passing in the network definition and the config. This returns the serialized engine. You just save that binary data to a .engine file on disk. That's your optimized asset.
Done. Engine file created. Now, the fast part.
Step 3. Run inference, runtime. First, you load that save.engine file using trt.runtime.deserializeCUDA engine. This gives you back the iCUDA engine object. From that engine, you create an iExecution context. Now you need to manage memory. You'll allocate memory buffers on the host, CPU, and the device, GPU, for your input data and for where the output results will go. Libraries like PyCUDA are often used here.
Right, got to move the data around.
Yep, so you pre-process your new input image, maybe resize and normalize it. Then you transfer that input data from the host buffer to the GPU device buffer using something like CUDA.mex pytodesync. The async is important for performance. Then you tell a context where its input and output buffers are on the GPU using context.setAndSortAddress. Now the core step, execute inference with context.execute async v3. This runs the optimized engine asynchronously on the GPU.
Asynchronously, okay.
Then you copy the results back from the GPU output buffer to the host buffer using CUDA.memspeed.sysync. And finally, because those operations were asynchronous, you need to synchronize the CUDA stream using stream.synchronize to make sure everything is actually finished before you try to use the results on the CPU. After that, you can post-process the output tensor, maybe find the highest probability class index, and print your prediction.
Wow, okay. That's a clear path. Export, build, run. That core workflow sounds incredibly powerful already. But you mentioned even more advanced techniques for squeezing out peak performance. Let's dive deeper into precision engineering.
Yeah, this is where things get really interesting, especially leveraging that specialized hardware. FP16 precision, or half-precision floating point, is often called the easy win. It offers substantial speed up over FP32, often doubling throughput or more, with usually a negligible impact on accuracy for many models.
Negligible impact. That sounds great. How do you enable it?
If your GPU platform supports fast FP16 math, which most modern NVIDIA GPUs do, enabling it is typically just a simple flag in the builder configuration during the build phase. Something like config.setFlag, trt.builderflag.fp16, boom, free speed boost, basically.
Nice. The easy win. What about the next level?
Then there's INT8 quantization. Using 8-bit integers, this is often called the ultimate speedup. It dramatically reduces memory bandwidth requirements because the data is smaller, and it fully utilizes those tensor cores we talked about, often giving another big jump in performance.
Ultimate speedup sounds tempting, but there's a catch, right? You mentioned accuracy loss.
Exactly. There's the catch. If you just naively convert everything to INT8, you could lose a lot of precision and your model's accuracy can plummet, sometimes significantly.
So how do you get that phenomenal INT8 speed without crashing the accuracy? That sounds like the major hurdle.
You're hitting on the biggest challenge with INT8. This is where post-training quantization, PQQ, comes in, and specifically a process called calibration. Calibration is where TensorRT learns the dynamic range, the distribution of activation values flowing through your network.
How does it learn that?
It does this by running a small but representative subset of your original training or validation data through the model in FP32 precision. Usually just a few hundred samples is enough. Based on observing these real activation values, it calculates optimal scaling factors for each tensor in your network. These factors map the wider FP32 range to the limited INT8 range, which is typically -128, 127. The goal is to minimize the information loss during this mapping.
Okay, so it needs real data to figure out the best way to shrink the numbers. How does a developer implement this?
Right. Developers need to implement a custom calibrator class. You inherit from TensorRT's treat.int8 calibrator base class. Often you'll use treat.int8 entropy calibrator 2, which uses an entropy-based method to find scaling factors that try to preserve more information, often leading to better accuracy. This custom class needs a few key methods. GetBatchSize tells TensorRT how many samples are in a calibration batch. GetBatch is the core method where you load a batch of your representative data, pre-process it, and copy it to a GPU buffer that TensorRT provides. And importantly, there are methods like read calibration cache and write calibration cache. These let you save the calculated scaling factors to a file after the first calibration run.
Ah, so you don't have to recalibrate every single time you build the engine.
Exactly. Calibration can be time-consuming because you're running data through the network. Caching those results saves a huge amount of time for subsequent builds.
That's a sophisticated process. Very cool. Beyond just messing with precision, what other kinds of automatic optimizations does TensorRT offer? Things developers don't necessarily have to manually code.
Yeah, there are some powerful graph optimizations that happen under the hood. Layer and tensor fusion is a big one we touched on. TensorRT automatically merges sequential layers. Remember the example. A convolution, followed by adding a bias, followed by a real U activation. TensorRT might fuse those into a single CBR kernel. That's vertical fusion.
Fewer steps, less overhead.
Precisely. Or if you have multiple layers that take the exact same input tensor, it might fuse them horizontally. The result is fewer individual kernel launches on the GPU, which reduces overhead, and less data movement between operations, especially less movement to and from slow off-chip memory. If you ever use a profiler like Nsight Systems on your TensorRT engine, you'll actually see fewer, larger kernels running compared to the original model definition. That's fusion in action.
So it simplifies the execution graph. What else?
And then there's that kernel auto-tuning we mentioned. For every common operation convolutions, matrix multiplies, pooling TensorRT often has multiple different ways, different kernel implementations to perform that operation. During the build phase, it actually benchmarks these different options on your specific GPU hardware and picks the fastest one for that layer's specific parameters like filter size, stride, etc. It's like having a performance engineer constantly tweaking your code for your exact setup.
That's incredibly smart. But what about models that need to handle different input sizes? You know, in the real world, you might get images of varying resolutions, or maybe you want to process different numbers of inputs at once, different batch sizes. Fixed input shapes often feel like a straitjacket.
Yeah, stepping back, that's a very common real-world challenge. TensorRT addresses this with dynamic shapes. And the way you enable this is through something called optimization profiles. For each input tensor that might have dynamic dimensions, like the batch size or maybe image height and width, you define 3 configurations in an optimization profile.
3 configs.
Yep, a minimum set of dimensions, an optimal set, and a maximum set. For instance, let's say we want our ResNet 50 model to support a dynamic batch size, maybe from 1 up to 16, but we expect it will most often run with a batch size of 8. You'd create an optimization profile and set the input tensor's shape range, like min 1, 3, 224, 224, ops 8, 3, 224, 224, and max 16, 3, 224, 224. The 3, 224, 224 are the fixed channel, height, and width.
Okay, so you define the boundaries and the typical case.
Exactly. The optimal shape is particularly important because TensorRT uses that shape when it does its kernel auto-tuning during the build phase. It optimizes primarily for that expected common case. You add this profile to the builder configuration before you build the engine. Then at runtime, before you call execute esync3, you explicitly tell the execution context what the actual input shape is for this specific inference call using context.setInputShape. This allows that single compiled engine to efficiently handle inputs within the defined min-max range.
Very flexible. Okay, this all sounds quite theoretical, building up these layers of optimization. But the sources, they include a capstone project that brings it all together. What real-world problem does it tackle? What's the core objective?
Right. This project is great because it really synthesizes everything we've discussed. It takes a state-of-the-art YOLO-8 object detection model, models that draw bounding boxes around objects in images or video. And the goal is to build a high-performance inference pipeline for real-time video streams using this YOLO-8 model. So that involves converting YOLO-8 from its original PyTorch format to TensorRT, testing it across different precisions FP32, FP16, and importantly INT8, and then building a Python application to actually run it on live video. And crucially, measuring both the performance, like frames per second, FPS, and the accuracy, using the standard metric mean average precision, or MOP.
Okay, object detection on video. What do you need to start?
You'd typically need a pre-trained YOLO-8 model file, something like YOLO-8n.pt. The N stands for nano, one of the smaller variants. And you'd need a data set for calibration and accuracy testing. Usually the KCOCO 2017 validation data set is standard for object detection tasks.
Got it. Model, data. So walk us through the actual steps someone would take to pull this off. It sounds involved.
It involves several key steps, yeah. First, export YOLO of 8 to ONNX. The Ultralytics library, which is commonly used for YOLO models, actually makes this pretty straightforward. You can often just call a function like model.export format on dynamic true. Setting dynamic true is important here to handle variable batch sizes, which you often get in video streams.
Okay, ONNX file ready.
Second, you might do some rapid benchmarking with TriTexSec. Before writing any custom Python code for the pipeline, you can get a quick performance baseline using this command line tool that comes with TensorRT. For example, you could run something like tretexec on SEO8n.onNSX, save engine, YOLO of 8n mfp16.engine fp16. This command will build an fp16 TensorRT engine from your ONNX file, save it, and run benchmarks, giving you immediate insights into potential latency and throughput. It's great for a quick sanity check.
Nice. A quick preview.
I remember the first time I ran tritexec on a model, seeing those initial FPS numbers. It instantly validates the power of TensorRT. It's quite motivating. Third step, and this is usually the most challenging but also the most rewarding part, is building the INT8 engine with a custom calibrator.
Ah, the calibration process again.
Exactly. You'd implement that custom YOLO of 8 calibrator class, inheriting from Trot Entropy Calibrator 2. This class needs to handle loading batches of images from the COSIO dataset, pre-processing them correctly for YOLO of 8 haze, which typically involves resizing to something like 640 by 640, normalizing pixel values, converting from the common height width channel format to the channel height width format that GPUs prefer, and adding a batch dimension. And then it needs to feed these pre-processed batches to TensorRT via the getBatch method during the calibration process. You'd also use the caching methods here.
Okay, INT8 engine build, hopefully accurately. What's next?
Finally, you build the inference pipeline application. This is typically a Python script. It uses a library like OpenCV to read frames from a video file or camera stream. For each frame, it pre-processes it just like you did for calibration. Then it runs inference using your loaded TensorRT engine, could be FP32, FP16, or INT8. After inference, you get raw outputs from the model. For YOLO, this requires complex post-processing. You need to decode the raw tensor outputs into meaningful bounding boxes, class probabilities, and confidence scores. Then you usually apply non-maximum suppression, or NMS.
NMS, what's that?
NMS is a crucial step to filter out overlapping bounding boxes for the same object. A model might detect the same car multiple times with slightly different boxes. NMS picks the best one and suppresses the others. After post-processing, you can draw the final bounding boxes and labels onto the video frame using OpenCV, display the annotated video stream, and calculate the real-time FPS you're achieving.
That's a comprehensive pipeline, from video frame in to detections drawn on the frame out. Performance, of course, the FPS is one thing, but accuracy is another entirely. How do you quantify success? How do you make sure your super fast optimized model is actually, good?
Right. A 1000 FPS model is absolutely useless if its accuracy is 0. It has to detect the right things. That brings up the crucial point of validation. We must measure and confirm the accuracy. The standard metric for object detection tasks like this is mean average precision, MAP.
Okay, how do you calculate that?
You typically use a standard library like PyCocoTools, which works with the SOCOHOA dataset format. The process generally involves, first, iterating through the entire COCOCO 2017 validation dataset. For each image, you run inference using your built TensorRT engine, say the INT8 version. You collect all the predictions from your model across all validation images, the bounding boxes, the confidence scores, the predicted class IDs for every detection. Then, you need to format these predictions into a specific JSON file structure that the COCO file evaluation tools expect. Finally, you use the PyCoCoCotools.cocevil class. You load your generated results JSON and the ground truth annotations for the validation set, and it computes the official AFI score, along with other related metrics.
Okay, so it's a standardized way to compare your model's output to the known correct answers.
Exactly. This gives you that single crucial number, the MAP score, that tells you how accurate your optimized model is compared to, say, the original PyTorch model or the FP32 TensorRT version.
And what kind of results, what kind of trade-offs would we typically expect to see from a project like this, comparing PyTorch to the different TensorRT precision levels?
Yeah, the results usually paint a really clear picture of the value and the trade-offs. Your baseline, maybe PyTorch FP32, might have, let's say, an engine size of roughly 13 millibait and achieve around 37.0 MAP on the COCO dataset. Performance might be, I don't know, maybe 30 FPS on a particular GPU.
Okay. Baseline established.
Then Tensor FP32, you usually see a modest speed up, maybe 40-50 FPS, just from TensorRT's automatic graph optimizations like layer fusion and kernel auto-tuning. The engine size and MAP would be very similar to the PyTorch baseline.
A nice little boost just from switching.
Yep. Now, Tensor at FT16, this is often the sweet spot. The engine size drops significantly, maybe down to around 7 millibit. The performance boost is usually substantial. You might see FPS double or triple, maybe hitting 100 plus FPS. And the drop in MAP is typically very small, often negligible, maybe 36.8 MAP instead of 37.0.
Wow, big speed up, tiny accuracy cost. That does sound sweet.
And then Tensor INT8. This gives you the smallest engine, perhaps around 4 millibit, and potentially the highest throughput, maybe pushing 150 FPS or even higher. However, its accuracy is critically dependent on the quality of your calibration step. If you did a poor job with the calibrator implementation or used unrepresentative calibration data, you can hit a performance cliff.
Performance cliff.
Yeah, where the accuracy just drops dramatically. Maybe your MAP falls to 30.0 or even lower, rendering the model pretty ineffective despite its incredible speed. Successfully building an INT8 engine that maintains a high MAP, say staying within maybe 1–2% of the original FP32 baseline MAP, that really demonstrates true mastery of TensorRT and the calibration process.
That truly shows the power and the nuance, especially with INT8. It's not just about speed, accuracy is paramount. Okay, we've gone from understanding the core challenge all the way to these deep optimizations in a real-world project. What's next? What if you encounter a custom operation, some weird layer in your model that TensorRT doesn't natively support? Or what if you want to deploy this super fast YOLO8 engine at true enterprise scale?
That's an excellent question because, yeah, real-world models often have unique custom layers that aren't standard. If TensorRT's OnNX parser runs into an operation it doesn't recognize, it offers the powerful plugin API. This basically lets you write your own implementation for that custom layer. It usually involves writing a custom CUDA kernel for the layers forward past the actual computation on the GPU.
Writing CUDA, that sounds advanced.
It is more advanced, yeah. You write the CUDA kernel and then you wrap it in a C++ class that inherits from TensorRT's plugin interfaces, like iPlugin v3 and iPlugin Creator v3.1. This allows you to register your custom layer implementation with TensorRT so it can integrate it seamlessly into the optimized engine graph. NVIDIA provides resources for this, like their official TensorRT open source plugin repository on GitHub, which has examples and code samples like Sample Onyx, MNest, and the TensorRT distribution.
Okay, so there's an escape hatch for custom stuff, even if it requires more effort. What about deployment? Going from that engine file to production.
Right. That optimized.engine file is powerful, but it's not a full production solution on its own. You need a serving infrastructure. NVIDIA Triton Inference Server is really the go-to solution here. It's a production-grade inference serving platform designed specifically to deploy TensorRT engines, and other formats too, at scale. You basically set up a model repository on your server. Inside, you place your .engine file and a simple text configuration file, usually called config.pbtxt. This config tells Triton things like the input-output tensor names and shapes, maybe enables dynamic batching on the server side.
And Triton handles the rest.
Pretty much. Triton handles creating HTTP and gRPC endpoints for receiving inference requests, managing request queues, scheduling inferences onto the GPU or multiple GPUs, handling concurrent requests efficiently, and sending back the results. It takes care of a lot of the operational complexity.
Okay, Triton for general serving. What about the video analytics case?
For video analytics specifically, your TensorRT engine integrates perfectly into an NVIDIA DeepStream SDK pipeline. DeepStream is a GStreamer-based SDK, built for creating high-performance, hardware-accelerated video processing pipelines. In a DeepStream pipeline, your TensorRT engine would typically function as the primary inference plugin, often using the Infer element. It takes video frames, runs your YOLO8 engine, and then passes rich metadata like the detected bounding boxes, class labels, confidence scores downstream to other pipeline elements. These could be object trackers, other secondary inference models, or video encoders.
So it becomes one component, albeit critical one, in a larger specialized video processing flow.
Exactly. Understanding where your highly optimized TensorRT engine fits into that complete, scalable, and maintainable AI system, whether it's served via Triton or embedded in a DeepStream pipeline, that's really the final step. It's about transitioning from just being a model optimizer to thinking like a full-fledged ML systems engineer.
What an incredible journey we've been on. Seriously. From truly understanding the unique demands of AI inference, which are so different from training, to mastering TensorRT's precision engineering like FP16 and that tricky INT8 calibration, its clever automatic graph optimizations, handling dynamic shapes, and then seeing how all these pieces come together, how they culminate in a real-time high-performance project like the YOLO8 example.
Indeed. It's quite a path. This deep dive hopefully has shown you how you can unlock really incredible performance for your AI models using these techniques.
Hmm.
And I think the ability to co-optimize thinking about precision, but also about things like sparsity and the underlying hardware architecture together, it's really going to define the next generation of AI performance engineers, especially as models just continue to grow in complexity and scale.
So what does this all mean for you, our listener? Well, it means the path forward in high-performance AI is just rich with possibilities. There's always another layer to optimize, another technique to explore. For instance, consider exploring hardware-aware sparsity. Like NVIDIA has this thing called 2.4 structured sparsity. It's a way to prune redundant weights in your model, but in a specific pattern that the hardware, the tensor cores, can actually accelerate directly.
Right. It's not just making the model smaller, but making it smaller in a way that the hardware understands and can leverage for more speed.
Exactly. It's fascinating stuff. It hints that the future isn't just bigger models, but smarter, more hardware-aware models. We really hope this deep dive has given you a powerful shortcut, a solid foundation for getting well-informed about high-performance AI inference with TensorRT. Until next time, keep exploring, keep learning, and definitely keep asking those deep questions.